السلام عليكم ورحمة الله. إن شاء الله في هذا التسجيل راح نحكي نوع من التفصيل عن ال Frequency Response of LTI Systems. في البداية if I have a transfer function h of z, I can find the frequency response مباشرة. If I substitute z by e to the power j omega, then I can get the transfer function. Given that the ROC, the region of convergence, contains the unit circle, which is this substitution. So those two statements are equivalent, right? Okay. One note here to take into consideration that the frequency response is periodic. This is due to the periodicity of the complex exponential, right? So we can, if we add 2 pi k is an integer value, and then we can separate the exponentials, and this exponential actually this equals to 1, and we return back to the original frequency response. Okay, now the frequency response, as it is the case for the transfer function, it is a complex quantity, so we have two relevant or corresponding quantities. The first one is the magnitude response, second one is the phase response. Okay, we get the phase response by looking into the argument of the complex exponential, whereas the magnitude response is the magnitude of the frequency response. Okay, another relevant quantity is the group delay, which is simply the derivative of the phase response multiplied by minus 1. Okay, the physical meaning of the group delay, it's simply, you can say it's the number of samples, roughly speaking, that the output is being delayed. So it's the delay between the input and the output. In filter design in general, we like a constant group delay or a linear phase response here. Okay. Another important topic in the frequency response is the frequency bandwidth. We will discuss bandwidth in more details in the upcoming chapters, but here we can roughly say that the bandwidth for the case or the simple case of low pass filtering is the frequency bandwidth. When I say frequency, I mean the angular frequency omega. Okay, so it is the frequency range or frequency bandwidth that goes through the system unaltered, unprocessed in a general sense. Okay, so we have two main types or definitions of the frequency bandwidth. The first one is the -3 dB bandwidth, and the second one I will call it first null bandwidth. First null bandwidth. The first definition, which is the -3 dB bandwidth, it is the frequency range. So here we are we are looking at usually the magnitude response. Okay, so here we're looking at the frequency range until the power. So this is, let's say this is omega c, and this is the bandwidth b. So this is the frequency range from the DC value to a certain cutoff frequency where the power is reduced to 1/2, which is -3 dB in log scale, and the magnitude it will equal 1 over the square root of 2. Okay, as for the first null bandwidth, it's an easier definition. It is an easier definition. again we are investigating the magnitude response. Sorry. Case here. So we are looking at the frequency of the first null, meaning that the frequency response or magnitude response reaches a zero value. Okay, from 0 dc or from 0 hertz, which is, or zero angular frequency, 0 radians, till the first null that we encounter here. Okay, so let's take an example. So we want to consider the 2-point moving average filter below, which has this form, right? And we want to find the following: the frequency response, the phase response, the group delay, and the first null bandwidth. Okay, so the first thing to do here is to use the Z transform. So we take the Z transform of both sides of the equation, and this will give us this equation, right? We can take the x of z as a common factor here, so we get this term like this, and if we divide both sides by x of z, we get the transfer function by definition. So this is the transfer function of the 2-point moving average filter. Now if we want to find the frequency response, we simply replace z by exponential j omega. Okay, now in this form it doesn't lend itself to analysis, so we perform a little algebraic trick. We take as a common factor exponential minus j omega by 2, so we get this term here. This equals actually the cosine of omega by 2, right? Now this expression, we can easily say, okay, this is the magnitude response and this is the phase response, minus j omega by 2. Okay, so we take the magnitude of this, right? Remember that the magnitude of the exponential omega j omega by 2 equals 1, right? So we're left by this one, this term I mean, and here we have the phase response. Now if we take the minus, so this, if you recall, the group delay is minus the derivative with respect to omega of the phase response, which is 1/2. It's a constant, so this is a linear phase system, right? So let's look into now, or let us find the bandwidth okay. The first null bandwidth, so we need to find omega that will give us a value of 0 here. It's simply omega equals pi radian, so the first null bandwidth is from 0 till pi. Okay, now let's take another example here. It's a 2-point IIR filter, right? So see, we have the current output depends on the previous output and the current input, again we need to find the frequency response, the phase response, the group delay, and this time the minus 3 dB bandwidth, because as we shall see in a few seconds or a few minutes, that it is maybe we cannot find the first null bandwidth, right? So we have to go to the best second option available, which is the minus 3 dB bandwidth. Okay, so we go through the same steps. We take the Z transform, and here we take, this time we take Y as a common factor, right? So we have 1 minus, this time Z to the power minus 1 equals X of Z, right? So here, which is Y of Z over X of Z will equal 1 over 1 minus Z to the power minus 1. Okay. As for the frequency response, we substitute Z by exponential j omega. We get this term, right? So this is an IIR filter, right? Because it has a pole in the denominator. We use the same trick. We take exponential minus j omega by 2 as a common factor. Now this turns to 2 cosine omega by 2, right? And this is actually the cosecant, sorry, the secant of omega by 2. So if we take the magnitude, we get this term, right? 1/2 times the magnitude of the secant omega by 2, and the phase response is simply omega by 2. The group delay follows as the minus derivative of the phase response. We get minus 1 over 2, which is 1/2, minus 1/2. As for the finding the minus 3 dB bandwidth, okay, we now equate the magnitude to the half power value, which is 1 over square root of 2 this time, right? Let us square both sides, and then redefine the secant by the cosine, arrange the terms and take the square root of both sides, and only consider the positive value of the output, since we are looking into the positive side of the bandwidth, right? Solving for this equation, we get simply pi over 2. So the minus 3 dB bandwidth in this case is pi over 2. Now if we want to find the first null bandwidth, we want to equate this. Let's say, let's put it here, right? So we say, okay, 1/2 magnitude of secant omega by 2 equals 0. So we take out the 1/2, and we say, okay, it's 1 over cosine omega by 2, right? So if we flip both sides, let me just put it in a clean way, okay? Here as well, right? So this is not very clean. Okay, this should be cosine omega by 2 equals 0. If you flip both sides, right, you get cosine omega by 2, it tends to infinity. So in this case, you cannot find the first null bandwidth. So you have to find the minus 3 dB bandwidth, right? Okay.